Oh well, there you are. You're on even before you were supposed to be. I think we had a little technical glitch, but I guess it doesn't matter. Hi Kim, thanks for being here. I am Brian Malow, and this is But Seriously. And through some just technical glitch, we're meeting our guest before we were gonna. I was gonna say, stay right there, don't go away. I was gonna say that light. Today's show is really about light. And what an amazing thing light is, and how strange and wonderful and beautiful, and the source of so much information. 24/7, all day and all night, light is raining down on the earth across the entire electromagnetic spectrum and literally from across the universe. We're a little limited by our own visual range of our vision and the part of the spectrum that we see, what we call visible light, very human-centric there, what we call human visible light. But there is light raining down from every part of the spectrum, and remarkably, from each part of the spectrum, we're capable of learning different things about the universe. So my guest, and since we did just say that's my guest today, is a specialist in this field of turning that light that falls down on the earth invisibly to us into incredible imagery. She's a visualization scientist, and she works on the Chandra XRay Observatory. Kim Arcand, Dr. Kimberly Kowal Arcand, thank you for being here.
Hi.
Yeah, so sorry about that. That flustered me a little because some weirdness happened. Everything's acting weird today. It's just one of those days, I think.
It's one of those days.
You said that you were, you in your world, you're dealing with having a new puppy along with your dog that was already master of the house, I guess.
And they're both barking in the background, so hopefully you can hear me at all.
Yeah, so this is so cool because we've followed each other on social media for years. I don't even know how long, and maybe occasionally exchanged a remark or two, but we just really met this past week, and thank you so much for agreeing to be here. So you've had a really interesting path to where you are now. So you didn't jump in. You're not an astrophysicist, for instance, but I do understand that you always wanted to be an astronaut.
I did, yeah. I actually just loved the idea of science when I was a kid. I wanted to be an astronaut. I wanted to be a doctor. I wanted to be a veterinarian. I wanted to save the world and be an environmentalist. I mean, you name it. I think I just really like the idea of figuring things out, helping people, helping things around me. And I went to university with the idea of studying things under a microscope. And that did not proceed as planned. And instead, I ended up working with data that comes from some of the largest telescopes. So I guess you
Things
just never
that don't
know
fit
how things
under
will
a
end up.
microscope.
Certainly don't fit under a microscope.
Galaxies and supermassive black holes do not fit under a microscope.
They sure don't.
But telescopes, now we're talking. So yeah, you have a background in molecular biology, right? And then,
Yep.
but you got your master's in public humanities. And is that different from
Mhm.
just humanities? What is public humanities?
It is. So public humanities is all about sort of like the end user, right? It's all about the information exchange with other people. And particularly, I was very interested in ethics of data representation, even more specifically than that, since that is kind of the area that I was working in. I had already worked on a master's in computer science. So I was sort of threading together these different areas of interest to make a cohesive background that would help me make the most of the type of data that I get to work with every day.
I mean, but did you know, so at what point, you didn't know where you were quite headed then when you were, I mean, could you have imagined that you were going to be doing this, working with this amazing telescope in space, looking into the depths of the universe?
No. So when I finished my undergraduate work in molecular bio, I think then I realized like, all right, I really don't want to do this. I had been working computer science as like a work study program, and just found I was really good at and interested in using computers and using computer science to kind of tell the story of other scientific data. And that combination of skills is what brought me to work for NASA's Chandra Observatory. And then once I was there, I kind of saw perhaps areas of interest that I thought I could improve on. And then I did a couple grad programs because I thought it would really help me understand things a little deeper, and be able to talk about them a little better. And honestly, I'm just a total nerd at heart who loves learning. So
Yeah.
I spent most of my life in school and enjoyed it.
Excellent. So, let's talk about Chandra. So, well, first, you're a visualization scientist. So, what exactly is that? Because that's where you got your PhD. After molecular biology, public humanities, you taught computer science courses, and then you got your doctorate in visualization science. So, what is visualization science?
I like to think of it as telling stories with data. So that data that I'm working with now comes from these, massive telescopes in space primarily, and journeys to us. And when it gets to us, it's got to be sort of unpacked. It's not it's not a space selfie, right? We're not just snapping photos like you would with your phone. So you have to translate it from one form to another. And so I think of visualization science as just that process of transformation from the raw data to something else, usually a visual, but it could be a sound, it could be something you touch, it could be something you explore in virtual reality.
Excellent. And tell me about Chandra then. So your position is with the Harvard Smithsonian Astrophysical
Observatory. It's a mouthful.
Observatory. Yeah, yeah. And I mean, Chandra, tell me about the relationships there between, I guess, the Smithsonian and NASA. I know NASA partners on these projects with all sorts of other entities. So, what is the Chandra
Exactly. Yeah.
X-ray Observatory?
So the Chandra Observatory is one of NASA's great observatories. It's kind of like a sister telescope to the Hubble Space Telescope, right? So it was Chandra, Hubble, and Spitzer as sort of three of the great observatories out of four for a while. Spitzer retired not that long ago. And so now it's kind of Chandra and Hubble, and now the recently launched James Webb Space Telescope as well. And the idea behind the great observatories was to have a really multifaceted view of our universe in all different kinds of light. So Chandra has been studying X-ray light for 23 years, just about, and essentially gets to look at things like exploded stars, areas around black holes, colliding galaxies, clusters of galaxies, young temperamental stars, and so much more. So it really is a very unique view of our universe in that high energy light. So Chandra, as a NASA mission, is operated for NASA by the Smithsonian. And the Smithsonian has a partnership with Harvard. So we're physically on like a Harvard campus, for example, for the scientists and admin and tech staff. And that's where kind of like a lot of the day-to-day operations take place. So NASA mission operated by the Smithsonian on Harvard campus. That's where they all
And where
kind
are
of
you?
line up. I'm actually home. So today I am zooming to you from Rhode Island.
Rhode Island.
And it is a beautiful spring day here in New England. So
And so, have you been working I guess the nature of your job means you probably can work remotely pretty often. Did it change because of the pandemic, or did you already sometimes work remotely?
So it did change. I think the pandemic, pretty much changed everything. But I have been working remotely on and off since my kids were born about 18 years ago. So I was very, very used to teleworking, working from home. But certainly aspects of the job had to change during the pandemic because everybody else started working from home, and daily meetings took way over what I had ever expected them to. And even the operations of the telescope itself, we really had to look carefully at the health and safety of the staff around that. Chandra is operating 24 hours a day. So there's really no break in its care, right? It needs to be monitored at all times. So there was a lot of really interesting work that the engineers and the scientific staff did to support the operations group specifically, to make sure Chandra stayed functioning and operating 24/7.
Yeah. And so where is Chandra? Because and you know what, we can
Yeah, maybe bring up the
oh
beauty
yeah,
shot.
yeah, it's like there, yeah,
Yep.
there's a nice
Hmm.
shot of
That's a good one.
the observatory. But Hubble is in orbit around the Earth, but the James Webb telescope I know was just placed in a different kind of orbit. It's I don't
Much farther
recall, but
out.
it's in
Yep.
like, yeah, it's so where's Chandra?
So Chandra is kind of in between the two, I guess you'd say, closer to the Hubble side. It goes about a third of the way to the moon at its farthest point. So it's in a very highly elliptical orbit around Earth, whereas Hubble clings a lot closer in a low Earth orbit. Hubble goes about a third of the way to the moon, so it gets a really nice, clear view of that X-ray universe around us without as many disruptions that it would have if it was lower down. So it gets a lot of observing time, and we check in with the telescope about every 8 hours to do downlinks or uplinks with NASA's deep space network, if
Network?
you
Yeah.
will, and that's how we get to communicate with it.
So I know that this is true, and it's with especially space telescopes that are on the lower end of the spectrum, whereas X-rays are very high energy. When you get down to the infrared and low, very infrared and long waves, then those telescopes have to be away from the Earth, and they have to they that any background heat can interfere with the sensor because it's detecting very low energy stuff. I mean, is that just true? Even though it's a different part of the spectrum and higher energy, does Chandra have to worry about that? I bet probably every telescope
No,
does.
so
No,
for
not so much.
Chandra, it's different. So Chandra does have to operate in outer space because our Earth's atmosphere has like a bunch of superpowers, I'd say. And one of those superpowers is that it protects us from many different kinds of light that we don't want. And one of those types of lights is X-ray light. We don't want X-ray light on our human beings and our animals and plants and all that because it really wouldn't be good or healthy for us. So the Earth's atmosphere really protects us from that, which means we have to go above the atmosphere in order to get that really clear view of X-rays that are being emitted from these objects throughout the universe. For Chandra, the important thing is the sun. Chandra is so super sensitive that if it looked at the sun, it would sort of burn its retinas out, if you will. Not that it has retinas, but you get the idea. So it really has to be careful. It has a solar shade essentially to make sure Chandra is always protected from those rays from the sun because that is so bright. It would just kind of destroy the telescope's very sensitive detectors.
Yeah, and we have this other image that points out,
Mhm.
just like most of the spacecraft that we send to Mars and all these other telescopes that we put in orbit, it has a lot of instruments on it. And I know that this might be a little adjacent to your area of specialty, but is there
Yeah, but it
anything you
is
can?
interesting.
You mentioned
Yeah,
there's a
I think what's
sunshade door. I
there
see.
is, and you can see that right up at the top.
Uh huh.
And I think what's interesting about X-ray telescopes is that the nature of having to capture X-rays is quite different than what we have to do to capture, say, optical light or infrared light. So, because their X-rays are so energetic, they have to go through what are essentially these barrel-shaped mirrors, which you can, I think, kind of see in some of the inset area that's going down right through the sort of the face of the telescope. Right after that, there are these barrel shaped mirrors that the X-rays kind of skip down. It's like if you went to a pond and you took a stone and you skipped it across the water. That's kind of the idea. You have like these grazing angles. So the X-ray photons, those packets of energy, can kind of skip right down through those mirrors and down to the detectors at the very end, where I don't know if you can read on the screen, but it says like the ACIS CCD imaging spectrometer, for example. And that's sort of where the magic then happens. It captures all of that sciencey goodness, and then it's packaged up in the form of binary code, ones and zeros, before it's sent on its way down here to us on Earth.
And then it has the solar arrays for to power it.
For
And
its
so
exactly. Yeah.
how how long has when was Chandra launched? How long is the mission? How far into it are we?
Yeah, so it was launched in July of 1999. So, and I started working for Chandra in May of 1998. So we've both been around for a while. And the original mission was essentially for like 5 years, and then it was extended to 10 years. And now I think we have like another 5 to 7 years left on our current mission. And hopefully we'll get extended again, assuming Chandra is operating beautifully and, efficiently still. That would be the hope, because even to this day, about 23 years later, essentially, Chandra is still the most amazing piece of equipment that can capture X-rays from space. You really can't beat Chandra's resolution. There's nothing like it yet. So it's important to hopefully keep Chandra operating for a while. And I'm not just saying that because I get paid, partly, only partly. But
It's
I
very
do really
important
think
that I
it's a
stay
very
employed.
important, it's very important, but also to keep capturing that really important data of our universe. So,
James Webb isn't a replacement for Chandra.
no, no, not, and it's really not a replacement for Hubble either. I think the benefit of the James Webb is that using that very special kind of infrared light, it can peer back super far, essentially into those really early stages of our universe when those first stars were forming, and to be able to see some of that, I think is really exciting, right? Like, I think one of the things I love most about my job is that every day I get to time travel from this chair, essentially, right? Without
Yes.
leaving my office, I can time travel as much as I want because I've got this fantastic view of our universe. But my view is like if you took a yearbook and all you saw of the graduating seniors would be their baby pictures, because you're seeing things as they were, not as they are. It takes light so long to travel across the ways to get to us, essentially, that it's always a glimpse in time. And I think that's really cool, because if we were somehow able to zoom out to these places now, things would look completely different. So yeah, it's like
Right.
we have our own little time travel box.
Well, you did just point out that you mentioned that the way James Webb will be looking in the infrared. And as I mentioned at the top of the show, it's so fascinating how, because of the different properties of light of different wavelengths, different frequencies, um, we can utilize them to learn completely different things. You can look at the same object. Like I don't remember, like some things, like some parts of light can travel through the interstellar medium or through gases and dust clouds, and others can't. So each part of the spectrum can tell you something else. Can you tell me
Yeah.
what so why Chandra, why X-rays, why do we even want X-ray eyes in the sky? What do
Yeah.
they tell us?
Yeah, it's a great question, because all of these different kinds of light, like you mentioned at the beginning, whether it's infrared light, whether it's optical light, whether it's gamma rays, X rays, ultraviolet, whatever, each different type of light gives you a very different picture of the universe around us. And it's kind of like having different tools in an astronomer's tool belt, and you take out the right tool that you need for the job. You don't take out a hammer if you need a screwdriver, right? So that would be a very bad project. Most likely you'd be, putting holes in walls that really don't need it. So the idea is, with like X-ray lights, we can really see through those clouds of gas and dust, for example, to peer into the centers of galaxies. Most galaxies in the universe have some sort of supermassive black hole at their core. And so to be able to peer through all of that gas and dust that you can't with, say, an optical telescope, for example, or perhaps an infrared telescope, to be able to get down to the nitty gritty of what's around that supermassive black hole, like we have in the illustration here that you just popped up on the screen. Really good timing. It's really important to be able to see things like that. So Chandra has been considered a black hole hunter because it can really narrow down using those X-ray light to be able to find black holes that we really hadn't been able to find before, and also to learn so much more about them, right? We now know things like black holes, supermassive black holes at the center of galaxies. They're not these cosmic monsters that they're necessarily made out to be. They're more like, ultimate recycling centers. They're responsible for like the care and feeding of the galaxies around them. So they do as much good as harm, I guess you would say. They're not just cosmic Roomba machines sucking up things as they go on their menacing way, right? They're kind of doing their own thing. They've got their own job. They're responsible for what that galaxy's environment is like. And I think that's pretty cool. Or hot, I guess I should say hot,
Yes,
since this is
very
all
cool
heated.
and very hot. Hey, what do you mean by
Right.
the care and feeding or whatever you just said? That
Yeah.
what role do black holes play? Are you saying in like the evolution of their environment of the galaxies that the supermassive ones are at the
Exactly.
heart of?
Yeah.
Yeah.
Yeah, exactly. So they're like these engines at the core, right? And I think there is this idea that black holes do nothing but suck things in. And while things absolutely, when you get too close to that gravitational pull, yeah, it's going to fall in, whether it's a snack like an asteroid or whether it's more of like a bigger meal like a star or two. So that absolutely does happen. But as things are getting close to the event horizon of the black hole, the sort of point of no return, lots of different things can happen. And supermassive black holes accrete or give off this stuff as well. So there are these massive, powerful jets that are ejecting different kinds of things outside of that black hole. And those jets are like a really massive recycling center, if you will, pushing things out into the galaxies, really steering up the material. So yeah, it's really useful for these black holes to be their sort of, they're stirring the pot, if you will, of all that material that's around them.
Yeah, I guess even though you didn't get an undergrad or PhD in astrophysics, you've had to learn a lot of astrophysics, right?
Yes,
In addition to,
a lot.
programming and everything else, you've had to pick up quite a bit to apply all your visualization skills. You've had to learn not only the computer
Right.
coding, but you've had to learn the astrophysics, right?
Right, because it can't be done separately, I find. You can't just like put up a wall between the science and the computer science. It's really a threading of the two together. And so I found that I have the best ideas and sort of outputs when I really understand the scientific information, at least on some level. Like I am not able to really parse like the deep thoughts of cosmology. I feel like cosmologists are like, they blow my mind, talking about how the universe formed. Like I can't even process that. It's like way over my pay grade. But I do find that having this understanding of things like black holes, exploding stars, pulsars, different kinds of gamma ray bursts, neutron stars, whatever, all of these exotic sounding objects, if you don't have some semblance of what's happening there, it's hard to understand or to know best what to do with that data to represent them, right? That's what I found at least. But again, lifelong nerd here, just like to learn. So maybe it's just that aspect of my
Yeah.
personality.
You know, that's amazing. And interestingly, the the cosmologists you referred to, they're dependent on this data that you help
They are. That's
that
right.
you're part of the team collecting and transforming it so that they can do that high level work that you were
All their
describing.
calculations
Yeah.
that make my brain go exploding. Yes.
I mean, I
So
love the
yeah.
play between theoretical physics and experimental physics, and how some discoveries come from one realm. Sometimes something is theorized, and it takes years or even decades, like the Higgs boson, theorized decades before we have the technology to look for it. And then other things are seen experimentally, and then turned over to the theorist to, well, explain that, right?
Explain it exactly. And I think that's a really good point. It's like there are these different, like three different strands of hair that have to be braided together, right? You have the theory, you have the observation data, and then you also have all the numerical calculations, right? That simulation information as well. So like those three different components, they're each threaded into like a braid of scientific information. And any one part of understanding the universe, it's impossible to do with just one of those strands of hair, right? It's like you need all of it to be able to figure these things out. It's pretty cool. But yeah, to even contemplate cosmology makes me want to like go run and
So
hide.
yeah, but I mean, what you're doing and the program. So you know what? Let's jump into that right now because I think it's fascinating that what you start with data that's just being sent from the telescope down to Earth as a string of ones and zeros, right? Like your data, and I queued this one up. Um,
Yes, yes. This is
so
essentially the data path, if you will, that we're looking at now.
yeah, so all you're getting is a bunch of ones and zeros. What do you have to do? How do you understand
Right.
that?
Yeah, it's like that, again, going back to like 1999 when we first started getting this data. And I honestly did not really know exactly what to expect and what like processing
Oh,
would be best for this kind of information. Oh yeah, there's a little sound piece in there. But what this compilation is showing is essentially all the possibilities, right? So X-ray data is invisible to humans, right? There's no human that can see an X-ray light. So we have to build these telescopes that can capture those X-ray photons, those packets of energy, and then we use computer science, essentially different coding languages, to be able to process it, to be able to like squeeze all of that lemon juice out of those really lovely lemons that we're able to capture, to be able to make something, whether it's a lemon pie or lemonade, who knows, right? And I must be thirsty because that's all I can think of right now. So yeah, it's really this process of taking those ones and zeros, that binary code that is essentially the suitcase that the information is packed up in to be able to come down through NASA's Deep Space Network, before it's unpacked here at one of our laptops, perhaps mine here in Rhode Island, or someone's up at the control center, wherever we might be. I think one of the cool things about this job is because our telescope goes a third of the way to the moon, you can kind of do this job from pretty much anywhere. But when you're unpacking that suitcase, you need to understand the scientific story that's underneath it. And that's where like I really rely on the scientists who requested that information, because scientists go through a system of proposing. They have questions that they want to find answers for. So they propose to the Chandra community to be able to get some time to look at XYZ object, and that's either granted or not granted based on the case that they made, and the like physical nature of being able to do that type of observation, what have you. And then when they first get their data, they really have to analyze it to get that scientific story to figure out what is happening in that cosmic phenomena. And then by the time it gets to me, there's already some kernel of what that story might be. And my team works with the scientists who requested it to be able to figure out what we need to do to be able to extrapolate all that sciencey goodness, to be able to then convert it into something that will help tell that scientific story, hopefully in a meaningful, but also pretty attractive, interesting kind of way. So oftentimes that's going to be the form of an image. It could be a two-dimensional image, for example. Like I think you have a bunch of images queued up of Cassiopeia A, if we wanted to look at one of those. This is an image of an exploded star, for example, of Cassiopeia A. It's one of the very first objects that we ever looked at with Chandra. And our first collection of information on this object was just 1 hour, and it was still beautiful. But the image up on the screen now has over 1 million seconds worth of observation time that's been concatenated together. And so when you have a two-dimensional image like this, you can
was this one
apply
of the
different
earlier
kinds of
ones, or
information. Yeah, this one actually is a most recent image from Chandra plus IXBI. IXBI is another X-ray mission that essentially measures polarization. So it's using X-rays, but for a totally different point. You can think of polarization when you think of like your sunglasses, that you might have polarized sunglasses and they help block the glare from the sun. It's kind of like the inverse. Scientists that are trying to study polarization are actually, they want the glare. So they're using that glare to be able to find out more about the process or the the mechanical like underpinning behind the event that's happening. So different kinds of X-ray telescopes or different kinds of telescopes in general tend to work together really well. I feel like all of astronomy these days is really multi-wavelength because you need to have all these different kinds of information to figure out those questions that are being asked. It's kind of like if you went to a baseball field and you looked out on the field and all you could see was just a tiny little sliver down the third base foul line, and you had no idea what the rules of baseball were. And you had to somehow figure out the rules of the game just by seeing the third base foul line. You would have no idea what the pitcher was doing, if there even was a pitcher. You wouldn't know that there's a first baseman. You wouldn't understand what people in outfield were doing necessarily. You'd only see the ball if it came in that one little area, right? So it'd be really hard to figure out what's going on. With astronomy, once you have different kinds of light, it's like all of a sudden you sit down in that stadium and now you've got the entire ball field in front of you. You can see all the players, you can understand like where the ball is going. You just get that complete picture. And if
Right.
you're trying to figure out, those answers to the questions, you need the complete picture. So it's all about understanding that scientific story, using the right tools to get that scientific information, and then representing it in a way that makes sense for the data.
Is your role in doing these visualizations for scientists or for the public or
Yeah,
both?
I would say for both. I would say primarily my favorite audience would be for non-experts if I had to pick favorites. And that's probably what the majority of my work ultimately does serve. But for sure, it's also working with the scientists as well. And there are typically different ways that you can visualize something, whether it's for an expert audience or a non-expert audience, that will impact the visualization that you're working on. But if you're visualizing something for scientists with the goal in mind of also serving the non-expert, you can usually come up with something really cool. And that's some of the work we've done, for example, on the Cassiopeia A image you showed earlier of the supernova remnants. We have been able to model that into 3 dimensions with a colleague, Tracy Delaney, who was at MIT at the time. And it was really useful to be able to model Cassiopeia A into 3 dimensions because scientifically it told us cool stuff, right? It told us that the explosion was kind of happening in like came apart in 2 pieces, if you will. And when you look at the 3D model of that object, you can really clearly map where things like iron is, where the silicon is, where the sulfur is, and you can mention it in, you can model it into 3 dimensions. And that tells you something new and exciting about that science story. But then once you have that 3D model, you can do so much with it, right? We ended up 3D printing it, for example, and working with students who are blind or low vision to be able to improve that 3D print. So what started out as a project to be able to visualize a scientific finding instead turned into a project at the end of being able to open up access to the data, because creating something in 3 dimensions just opened up a whole new world, dare I say universe, of possibilities of what we could do with that information, if that makes sense.
Right. And I don't know if I can go directly to some. We saw a little
Mm,
bit of imagery already of 3D printing, but you also have this VR aspect, which is
yes.
fascinating. So this is a visual. Is this Cassiopeia A as well? This
Yes,
is the
yes.
same.
This is the same object. Obviously, this is one of my favorite objects in the entire universe because I talk about it a lot. Um, I think one of the cool things
What do
about
we
it is
need to know? What
Chandra
is
looks at it a
Cassiopeia A?
lot.
What do we need to know about
Sure.
Cassiopeia A?
Let's back up. So
Yeah,
yeah,
yeah.
this is a really beautiful exploded star. So the fate of a star depends on its mass, and the Cassiopeia A star was much more massive than our sun, probably 8 to 10 times more massive than our sun. And when you get to that sort of mass, you are essentially getting to be a little bit unstable in your size, so that when you start running out of fuel, your core collapses and then you just explode your guts out all over the universe. So the Cassiopeia A supernova remnant is just that really beautiful stellar vomit, I suppose. And it's all of this material that's expanding out into the universe, into that sort of surrounding medium in the Milky Way galaxy. This object is about 11,000 light years away from us, or
Hmm.
light years a distance that light travels in a year, about 10 trillion kilometers. So it's actually kind of nearby, which makes it a great object to study, a great object to study with an X ray telescope, and Chandra specifically, because Chandra's vision is so sharp. So Chandra and Cassiopeia A have a really great relationship. They're like BFFs, right? And so once we had that 3D model of Cassiopeia A by working with the scientist Tracy Delaney that I mentioned, we just found all of these different use cases for it. And one of them was bringing it into virtual reality. So this was really cool because this was the first time observational data from Chandra, as well as the Spitzer Space Telescope and some optical data as well, was used to create a 3D model of an exploded star. And then this was the first time we were able to bring it into virtual reality. And this is just one of my students who's walking around and learning about that exploded star in virtual reality. So she's able to kind of like step inside it and find the neutron star at its core, the leftover bits of that star, and learn about where the iron is, which is the green, for example. What's cool about this is it's a really great way to understand that when a star like Cassiopeia A explodes, there's iron that had built up right at its core before the explosion. But now you can see that there are these huge pockets of it and the most outer parts of that remnant. So that means a star like Cassiopeia A essentially turned itself inside out when it exploded. And you can clearly see that when you're modeling it in 3 dimensions, which I think is very interesting.
I would think that you mentioned that the woman in that last scene was a student of yours. Does that mean she's like a data visualization?
More
Because
like, so yes, so at Brown, I have like a mini little lab, I guess I'd say, of students in the computer science department that work with me and one of the computer science managers, Tom Seguros, to be able to do these really interesting visualization projects. And the whole point to the whole reason that this collaborative began was because I was volunteering to mentor some high school students, I think it was, and I just walked into their VR lab at Brown. It's called a yurt. It's this beautiful structure where you can do virtual reality. And they had some data of Mars out, and that we were walking in it. And I was walking along Mount Sharp on Mars for the first time. And I was like, this is awesome. I have 3D data. Can we
yeah,
do something
yeah.
like that? And they're like, yes, indeed. And so we created this program, and I funded some students to be able to help take that data that we had and translate it from a plain 3D model into something that would work in virtual reality. And it began a whole new program. It was really
And
cool.
when you were creating this virtual reality version, who was the intended audience for that? Because as cool as it is for us, I would think cosmologists and other astrophysicists would love to see. There's one thing to know all the details about where the iron's create, but it's another thing to viscerally
Yes.
stand
Yes.
before it and rotate it and see it in 3 dimensions.
100%. I have been looking at data of Cassiopeia A since 1999. And the first time I walked inside it, the very first time we had a working demo at that lab at Brown, I was just completely shocked in the best way. It was just so interesting and so exciting to be exploring data in a completely different way. And people are just starting to do studies now to understand what the capabilities are of using virtual reality and other forms of extended reality as a tool for understanding the universe. At the time that we were creating this, it was an experiment, to be honest. That's kind of like one of the areas of research that I'm allowed to do, essentially. Figure out what the possibilities are for our data, what are new avenues we can take it down, what are different ways we can play with it. It's like I've been plunked down into a sandbox and given a whole bunch of like these different kinds of like toys and just said like figure out how to make a really awesome sandcastle. And I'm like, okay,
Yeah.
like, this will be great. But I think, I can really picture honestly in like 10 years time that there are researchers here in the US, researchers in Japan, wherever, all around the world, that are able to work in real time together in an extended reality space. Like right now, that's not as easy to do, but be able to get your data and for it to populate more automatically into a virtual reality, extended reality kind of space where in real time you can collaborate with your other investigators, be looking at things or listening to things together. That's kind of where my brain goes for like what the future of this work might be. So I think
Yeah.
of this early work in VR as like really important to just kind of lay some of that bit of foundation.
Have you had any? experience of an astrophysicist viewing data in this way and learning something new from it?
Oh, absolutely. At least anecdotally, I should say. I don't know if they've gone and written up papers about it exactly, but for sure, anecdotally, they've told me like, "Oh, I never noticed this before," and "Oh, this is really cool to see," and "Oh, this helps me think about this in a different way." And I think that last part is probably a really important part, that sometimes it's like enabling a new kind of curiosity or a new kind of creativity around data that you might be used to. Like, I'm very used to this data now. So being able to mix it up and understand it in different ways is great for me as a researcher, because it makes me think of new things that I can do. And I think that's similar for other researchers as well. If they're studying the astrophysical mechanisms, it just gives them sort of a new way to explore it that perhaps they didn't think of before. But I don't think I've seen any papers that mention that yet. So I
Right.
hope someday that happens.
Sure. You
It
know,
would be great.
let's say, we had a bunch of little comments came in of just saying hello, some nice comments on the Rihan. I'll tell you about, he asked what software I use, and and thank you, Chris Bono. Yes, it looks great. It's called Ecamm Live, and I can tell you more about it. So, hi, Fred. Thanks for joining us. Oops, never mind your question. What was Jennifer had asked about whether you're involved in collection or visual representation, and more the visual representation, but you're right there with the
Yeah.
team that's collecting it.
Sure. The telescope really does do a great job of collecting it. And it's a very cool system that we have for the engineers, the folks on the ground that actually, take the spacecraft to the doctor, if you will, that both keep it safe and healthy and also collect it, or tell it what to look at first, make sure it's doing that safely, and then be able to bring that back down to the ground. So that is a different area of expertise for sure. And my job is mostly after that's happening. Then I get to work with the scientists that are the ones requesting the data to figure out how best to then represent it.
Jennifer asks, are the VR models something that will be made available for the public to experience and learn about, or is it
Yes.
just for internal use?
No, everything we do, I'm very much a believer in open science. That is like a core value of mine. So anything that I'm doing, I am putting out in some public platform as quickly as I can. So all of our virtual reality modules that we've created in the past 8 years or so are all on the Chandra website, and I can give that URL, Brian, or we can wait. It's up to you if you'd
Yeah,
rather
we
me.
can mention it now, and I'm sorry I don't
Okay.
have it as a graphic, but where is it?
Sure. Yeah, it's at chandra.si.edu/VR. V as in virtual, R as in reality. And that's it. It's a pretty
Yeah,
easy URL to get to, or you could, I'm sure, use your search engine and find it.
yeah,
But they're
Chandra
all
VR stuff.
available, and we make them accessible to like smartphones as well. So you don't
Nice.
just have to have VR equipment to be able to view it. You can use a smartphone. You can even look at it on your desktop. But if you want it in some sort of like actual virtual kind of space, you can just drop your phone in like one of those Google Cardboard type of
Yeah,
viewers and look at it that way.
nice. So, you mentioned your interest in communicating. So, in addition, I always find this fascinating with scientists. The research itself, your work is a full time job. But do you do the communication for fun? Or do you feel like it's an important part? Or do you feel obligated to, or is it just a sense of joy?
Oh,
Why,
it's
like you?
definitely, yeah.
Yeah,
Communication is definitely a main part of my job, I feel like, because it doesn't matter who I'm communicating with, whether it's a scientist or a non-expert. Like, communication is, I feel like, 99% of what I do half the time, right?
yeah,
Everything I'm doing is making choices to be able to represent it in some way for someone. And as soon as there's someone in that equation, you're communicating. So yeah, I really think communication is very, very important. I feel very lucky. I'm sitting here in this office, and essentially it's like my window is not a window to the outside, although it is, and that's where this lovely light is coming from. It's also like a window to the universe that I have access to. I'm sitting in like this cathedral, and I've got these fantastic stained glass windows to be able to stare at all the time. And I have that front row seat. but I don't want like to be the only person in that front row. I really, really have a drive to be able to bring other people with me along that ride. I want to fill up the entire cathedral so that we can all look at that stained glass window. We can all take the time to feel like, how was this cathedral even built, right? Like those are the sorts of things that I want everybody to be able to do. And so having the ability to have other people get access to what I have is really, really important to me.
Excellent. And you've taken that to the extent I hadn't mentioned previously that you are the co author of several books. One of them is called Light. And
Yes.
so some seem to be at, I mean, when you say an adult audience, it could include people of all ages, but then you've also written at least one children's book. So, that doesn't look as good there, but it looks great there. So, you want to tell me about a couple of your books? And these
Yeah,
are all
sure.
available where people buy books.
They are indeed. Yes, your favorite booksellers, they're there. So yeah, I started working with my colleague Megan Watsky many, many years ago, and we've always sort of written articles together and done a lot of projects together, and we just really, really connect. And a literary editor actually saw one of our articles at one point and approached us about writing, and we're like, sure. And so we wrote our first book. Oh, gosh, I think it was back in 2012, perhaps. I mean, it was just a gentle introduction to the universe. And then light was another topic that we really wanted to sink our teeth into because so much fascinating stuff happens when you think about light. And
And
that's
I'm
what
sorry,
this book
was
was
that
about.
was that Light from the Void? Was that your first
No,
one? Nope,
that
you have
my
too
first
many.
book was your my first book was Your Ticket to the Universe. Light from the
Okay,
Void, though, is one of the most recent ones. That was a
okay.
book essentially that showcases, yes, many different kinds of light, but mostly all of the fascinating data that we've been able to capture because of Chandra. So that one's a really great look at some of Chandra's like best and brightest images over the past, 2 decades. And then most recently, I started just getting into children's books because I've always loved children's books. And I had written a story for my kids back like about 10 years ago on a very long, boring ride through New England when actually it was more than 10 years ago now, because I want to say my son was about 4 and he's 18. And my daughter was like 2. And they were like antsy in the car. And I started telling them the story of Goodnight Moon and they got bored. And then I made it into Goodnight Exomoon to amuse myself because I didn't think I could read it like one more time. And I thought it was fun, and I tucked it in a drawer, a digital drawer, and didn't think about it again until the first Exomoon candidate was mentioned in a paper a few years ago. And then I dusted this off, and the Smithsonian ended up publishing it for me. So, yeah, I
When you
think
say
writing
exo, so
books
that's
is just,
interesting. I'm not sure I'd heard that.
yeah.
So,
Oh,
it's
yeah.
only such recent times that we were finally able to detect exoplanets, planets around
Yes.
other stars, some of the nearer stars here in our galaxy. But you're talking about moons of exoplanets,
Yes.
exomoons of exoplanets, and I guess I hadn't heard that we had. I knew that we had made some headway in like examining the atmospheres of exoplanets by just that
Hmm.
little bit of the star's light that passes through what is such a tiny speck on our sensor. It seems impossible. It all seems impossible that you can do
It
that.
does.
But
It does.
detecting exomoons.
Yeah, and exocomets are also possible, right? But so yeah, the first candidate paper I think I saw came maybe 3 years ago, and it was something like the exomoon, so the moon orbiting the planet outside of our solar system. I think the moon was really large, like Neptunian in size, which made it, a possible way to find it because it was so large. I don't think that one was ever confirmed. But there was another paper that came out even more recently. I believe it was sometime this year, perhaps it was late last year, that was a second potential candidate for these exomoons. So no exomoon has been confirmed yet, but to even be at the point where we're thinking of findings that could be exomoons or exocomets, it's just incredible because, like you said, it's hard enough just to find exoplanets, right? And even the
Right.
most recent story from Chandra on an exoplanet outside of our galaxy in another galaxy far, far away blew my mind because it's such a needle in a haystack kind of problem, right? Really fascinating stuff. I love to think about what life might be like on some of these other planets. It gets me right back to my biology roots, of course.
And it's
So
great to talk
it's
about it
really
on
fun.
this level and then for you to turn it into a children's book.
Yes, yes. It was fun to write that story because it was just an homage, I guess, both to Goodnight Moon, which my kids and I had always loved, but also to this burgeoning field of astronomy and how important I think that kind of work really is. So yeah, it was fun.
And I have one. I know you have probably a couple more books, but Magnitude, the scale of the universe, looks like a great book.
Yeah, that was another book because we get so many questions on size, right? So, like the Cassiopeia A supernova remnant that I was showing you before, like I've printed that in a little tiny 3D print that you can hold in your hand, right? So you can hold a dead star in your hand. And people would always be like, well, what's the actual size? And I'm like, well, it's pretty big. You couldn't hold it. It's about 40 million billion times the surface area of our sun and planets. And if you're a Pluto fan, you can toss in Pluto. It doesn't matter at that math. But that is such a ridiculously large sounding scale. However, in the grand scheme of the universe, it's such a tiny little pinprick, right? So, this whole idea of scales, both really large and really small, they are so hard for us to grapple with because as humans, we only have our human frame of reference, and that's earthbound stuff, right? Even picturing the size of our sun is difficult to contemplate, and our sun is just an average size star, no big deal, right? So it's scale is really hard, and I was hopeful that some of the virtual reality work might actually help people understand scale, but even that, I think it's very difficult to be able to understand in a visceral way what some of these scales are operating at. So
Absolutely. So, there's something else fascinating in terms of, I don't even know if visualization is the right word, because more recently you've expanded into another sensory realm for helping us uh, visualize figuratively information. So, tell me
yeah.
what this is. Yeah, before we hear it. So, what is this image?
So this is one of my favorite images, which maybe does not seem likely because it doesn't necessarily look like all that much, but I think that's actually the exciting part of it. So this is the Chandra Deep Field South, and this is the deepest X-ray image ever taken. It's just kind of like a really dark patch of the sky that we used over 7 million seconds of Chandra observing time in order to catch, right? And if you're looking at it, it just looks like a black rectangle with a bunch of like multicolored confetti tossed on it, right? It doesn't look like much of anything. But when you hear the story, that essentially all of these dots are supermassive black holes or very active galaxies with supermassive black holes at their cores. And so you're looking at a field of essentially thousands of black holes. And this type of data really helps us understand the growth of black holes over like billions of years right after the Big Bang. So it's not only a massive scale in size because there's thousands of them, but also in time because we're going way back billions and billions of years. And the image, I feel like, just doesn't do the science justice. So during the pandemic, some colleagues and I had pivoted to using sound as a way of vivifying the data, to borrow a term from my colleague Gwen. It's not just about visualizing, but vivifying in a way that you can experience it in some new sort of way. And so what we did working with my colleagues, Matt Russo and Ender Santaguida, who have been working on what are called data sonifications for the past few years. I had been dabbling, but they were like really super into it and really talented about it because they also had music and sound backgrounds, which I do not have. So they took this data with me and we kind of looked at it to see how can we tell the story of these black holes. And so what you do is you're looking at this image, all of those different colors, they're essentially color coded by energy, with the lowest energy X-rays in red and the highest energy X-rays in blue. So what we did is attach sound to those dots according to the color, and it's in stereo. So as you scan from the bottom to the top of the data set, you're going to hear all of those different locations of those black holes and the energy levels that they're playing at. And Yeah, this is just really beautiful to listen to. I don't know if there are any people out there who are fans of Imogen Heap, but it kind of reminds me of her very beautiful work. And it's just fascinating to be able to listen to it. So I don't know if you can cue up the sound part of it.
Yeah. So what are we hearing?
So you're listening to thousands of black holes sing, essentially. And the way they're singing is just based on if they're super high energy X-rays or if they're lower energy X-rays. And so I don't know if people want to play around with these pieces of sound themselves. They can go to the Chandra website at chandra.si.edu/sound, and you can play all of the pieces. We've got a collection of, I think, maybe 15 of them by now. These little mini albums that we put out. We did it to be able to work with our colleagues who are blind or low vision during a time in the pandemic where we couldn't be with them physically looking at things like 3D prints and other kinds of models. So this way of attaching sound to data was a really interesting way of exploring how we could learn from our data in new ways. And it's interesting because sonification as a tool for research is also really important because the human sense of hearing is really good typically. So you can think of like the cocktail party effect in, I don't know, pre-pandemic times when people used to go to cocktail parties. You can be sitting on the couch with someone and having a conversation, but you can also hear someone in the kitchen washing some dishes. You can hear the front door opening as someone steps in. You can hear another conversation across the room, and you can hear in the dining room there's like a dog walking around, right? Like your sense of hearing can hear all of that distinctly and take all of the noise, if you will, and pick out the right signals that it wants to pay attention to. So in astronomy, there can be a lot of noise, and there are different kinds of science, like something called variable stars, stars that change very frequently, that when you're studying them, you're studying essentially light curves, plots of that information. And you can look at the plots, and of course you can study them that way, but you can actually hear the data sometimes better when you're listening to it versus if you're just looking at it. So there are always really new and I think exciting things that we can do with our data to really, yeah, just squeeze all of that sciencey goodness out of them and really figure out new ways to explore and hopefully new things to learn.
Nice. We had a few more comments. Let's see. Did you see the movie Ad Astra? Does the heliosphere distort Earth's ability to look deep into space?
I have not seen that movie, so I
Neither have
don't
I.
know. No. Yeah, I don't know. I'll have to watch it. I have a couple movies that I have to watch still. I did recently watch Don't Look Up. That was kind of depressing. Um,
Yeah.
but it was good to watch. I don't know. I couldn't find as much humor in it just because it felt kind of like, oh, sad.
Yeah, I
But
had
yeah, I
mixed
do,
feelings.
yeah, yeah. But it was interesting. And I have to say, I like movies like Contact is probably my favorite space movie. And I loved,
Hmm.
what was it, The Arrival with,
Arrival.
gosh, I'm forgetting. Yes, that
Arrival
was
is
so
beautiful
good.
about
I'm
the
forgetting her
linguist.
name. Yes, because I love that idea, right? Of having to be so interdisciplinary for that type of, yeah. Anyways, but I haven't seen Ad
Yes.
Astra. No.
No, neither have I. Jennifer says, does Kim have any of these images framed and hanging in her house? They're beautiful. Do you?
I do actually have some images hanging right there on my wall over to the
Nice.
side. Though those aren't framed technically, they're on like this little metal easel thing. But thank you. They are, I think some of them really are very, very lovely. One of my favorite images that's more recent is the Helix Nebula. I think, Brian, you might have that one
I do.
queued up. I don't know if we've shown that one already, but I think it's a great example.
Was it
First,
this
it's
one?
interesting. Yes, that is the one. It's very
What is that? It's
interesting to
beautiful. So
me,
many nebulae are so
right?
amazing.
So stunning. And what I like about this one is it is essentially like looking at a crystal ball of what our sun might look like in, say, like 4 billion years or so. And I think that's really cool to understand what our sun might do, puff off its outer layers essentially as it starts running out of fuel, as it's getting towards the end stages of its life. But it's also really interesting because this is showcasing off many different kinds of data. And just like I was talking about earlier, having all those tools in your tool belt is really useful. So we've got X-ray data here, we've got optical data, we've got, I believe, ultraviolet data, and I think we have a little infrared light as well. So all of these different colors are being combined to give a really stunning picture of what a future state of our sun might look like. I think that's pretty neat.
Pretty neat. So, Kim, this has been super fun, and I do want to ask you a few more questions, like
Sure.
about what drives you. So you said early on you dreamed of being an astronaut, and then you studied molecular biology. You picked up computer programming skills and some public humanities education, and then visualization science, and then having to not only utilize all your coding abilities, but then learn all this astrophysicist. What drives you? I'm always interested in what motivates people, what gets you up in the morning, and continuing to do what must be pretty challenging work sometimes.
Yeah, I think what I love about this type of work is there is something new every day, right? This field keeps you so humble because anytime you find the answer to like one question, you come up with like, I don't even know, 2 dozen more questions to figure out, right? And it's a type of science that you constantly feel like you know so very little. We know just a tiny, tiny fraction of the available information on the visible part of our universe. Never mind that like 95% of the universe is invisible, like dark matter, dark energy kind of stuff, right? We only know a little bit about that, like 5% of normal stuff that's out there. And it's such a tiny fraction that we're able to really contemplate and understand. So I think for me, it's exciting to work in a field that I constantly feel ignorant in the best way because I'm always pushed to learn something new, to learn something more. And that is a big drive for me. I think I would get bored very, very easily if I was in an area where that wasn't happening to me. So, yeah, I think that would be it.
And do you like that it's very collaborative too? You mentioned interdisciplinary work. I mean, this is like science and comedy for me. I'm interested in insect photography. I do for fun, and all of these things are at the intersection of art and science, which obviously you do a lot of work
Exactly.
at. But
Yep.
then it
Yep.
also includes all sorts of other disciplines.
Exactly. Yeah. And I love that. I love being able to work with artists and designers, with different kinds of scientists, programmers, engineers, you name it. Like it takes a village to figure out what all of this means. And I think that's really cool. There is a creative side to it. I don't consider myself an artist at all. I don't have any kind of skills, but I think I
No.
have an eye for stuff, right? I feel like I understand art in an interesting way, just not like I can't do any art myself. I can't do anything with paintbrushes or anything like that. But I love, I think, turning my lens on the universe and kind of, picking out the canvas, so to speak, and seeing what those paints might do, right? Like I have like an eye for it, but I don't have any artistic skill myself. So it is nice to be able to have a job that has a real creative side to it. Even if it doesn't sound like science is creative, it actually really is.
Can I ask you? This is a little outside of your specific work, but it's on the subject of visualizing astronomical data. Um, you know, I even hesitate to bring up the kind of skepticism of like moon landing deniers and flat earthers, which are probably a much smaller percentage of people than social media makes it appear. Hopefully, it's a much smaller percentage
Yes.
than the volume of their voice. But sometimes you hear people say when they see images of the Earth or see astro images, they 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 like in a critical way want to say, well, that's not real. That's not what you would really see. Is that a real picture of the Earth? Can you address can you address that?
Yeah, totally. Honestly, I get it. I think there's reason to be skeptical of things around you. I think it's reasonable to have a healthy sort of skepticism of things, right? You don't necessarily need to believe everything at face value. But I think the really important thing about this type of work is the idea of transparency because as I mentioned earlier, these are not space selfies, right? It's not click done. Everything, every step of the way has human involvement in it. The humans built the spacecraft that orbits a third of the way to the moon. The humans wrote the software that helps transfer the information. The humans do the coding that then translates it into another form, right? And there's a person like me or someone else that is at various stages of that data pipeline that are making choices, that are choosing to represent the data in certain ways. Now, in my case, I'm choosing to represent the data because I'm hoping to sort of bring that scientific story to the forefront. I'm not sitting there with paintbrushes coloring things by number. I'm not adding data. If I subtract data because it shouldn't be there, because it's an error or something like that, I clearly make a note of that, and that goes out to the public audience. But there is a person or people that are making those choices in the data representation to the final product that you eventually see or hear or feel. And so I think it's useful to understand, like, well, why did you make those choices? And that's the sort of thing that I do actually like to be very upfront about. I've written several papers on that exact topic because I think it's actually important to talk about why we make the choices that we do. And also, if you are making choices, to flip that around and to understand, if you're doing this for a non-expert audience, that those choices you're making will impact how they're perceiving that data, and to understand why. And that's sort of where the public humanities side of my work does come in, the ethics of data representation, if you will. So all of that is to say that I think skepticism definitely has its place, as long as it's not like a runaway conspiracy chain kind of thing. I think the idea of trying to always ask, well, why was that done? Or how was that done is a healthy thing. And those are the types of topics that, at least on the Chandra side, we really do like to talk about. There's tons of blogs, and all sorts of our data is encoded in the page, in the image itself, when we put out a release of an image, for example, so that hopefully that information is a little bit more apparent and transparent to the people that are trying to figure that out. So I don't know if that really answers your question, but I really do like to think of those things.
Yeah. And if we're talking about some nebula or something, it's something that's really colorful and interesting, and all of those different bits, those different colors, I mean, that's what our vision is doing anyway. We interpret different wavelengths of light as different colors. And
Right.
when you're visualizing that, you are taking different wavelengths and assigning them some colors to
Of
differentiate. So
course.
so that detail is there, even though our unaided eye might not see it.
Right,
It's not
because
fake
my
in that
job
sense.
essentially,
Yeah.
no, exactly. No, no, none of it's fake. I think it's
Yeah.
more like the idea of, why did you make that dress red versus blue, right? It's still a
Right.
dress, right?
Yeah.
Or why did you buy that car in white versus black? It's still a car. The car is not fake, right? But color for us definitely means something different, because my job essentially is to help make visible the invisible universe. And so human eyes can't detect any natural color in X-rays, right? So you have to assign a color to something that cannot be seen. So I think that idea of fake comes across because, well, for one thing, false color is applied. It used to be called false color. It's now used as representative color, because there is no natural color that humans can see X-rays in. So it's just like if you're looking at a weather map on the nightly news or on an app on your phone, and they've color coded the wind speed or the precipitation amounts or what have you, right? There is a color legend, and you know that that is being applied. Similarly, in this kind of X-ray data, for example, humans can't see it. So we always talk about what we are doing when we apply those colors. We always say what our color code is, because the idea is not to trick and deceive. It is to help add to the information quotient of the image. It's to take something that is invisible and make it visible. And color is one of the ways that we can do that. So, yeah.
Excellent. Well, this has been really fun and interesting, enlightening, one might say.
Enlightening. Ooh, good one.
I'm surprised no one said that
Great.
in a comment.
I know.
But
It's so true.
but thanks once again, and let me there's our Chandra X-ray Observatory that's out there. How much longer? What's its expected lifespan?
Well, it could keep going. There's really no expendables on board, so as long as it doesn't like get whacked by a meteor or something, it should be good for quite some time. I'd hope for at least another 5 to 7 years, if not 10. We'll see.
Nice. Right. Some spacecraft are powered by
Fuels. Yep.
some fuel,
Yep.
and but this is as long as the solar arrays are working, it has power.
We're good to go. Exactly.
See,
Yep. So
solar
it's all about
energy.
the healthy. Yes,
Solar
exactly.
energy.
Very important.
There's at least one environmental
All
message
comes
we
back.
got in there.
That's right.
And
That's right.
Kim, I want to once again, if people want to find you, um, at Kimberly Kowal at both Instagram and Twitter, you're pretty active,
Yes.
sharing images and science and what you're up to. So
Yep.
thank you very much. I really appreciate
Thanks.
you taking the time to talk to us.
Yeah, it was fun to
And
be
yeah,
here.
thanks. So thank you all for tuning in. That is our show today, and I want to thank Kimberly and the great people at the Chandra XRay Observatory. We have some great shows coming up. Our theme music is by Logan Whitehurst at loganwhitehurst.com. There he is, and you can also check out his artist page on Spotify. No more live shows this week, but we have some awesome stuff coming up in this next week. See you soon.